Hi everyone. So today what we're talking about is actually really similar to what we talked about yesterday. Yesterday we talked about exponential growth, and you'll notice that today we're just going in the opposite direction. We're going with exponential decay. So things are getting smaller and smaller, but still getting smaller faster than they would in a linear model. So the main difference between the equations we're looking at today and the equations we looked at yesterday are that in these equations, your growth factor is always going to be less than 1. Okay, so if you think about the ones we did yesterday, we were always like adding 100% to everything, and so our growth factor always ended up being like 1 point something. That's what would make it grow, is being larger than 1. Now we're working with growth factors that are smaller than 1, but still larger than 0, meaning we're not going to have negatives. Okay, you don't ever want to have a negative growth factor. That won't work for you. A couple of words you need to know for this lesson, just because it's going to come up in our word problems. First of all, depreciation. Depreciation is when the value of something decreases over time. So like a car depreciates because it loses value over time. The other one is half-life. The other one here is half-life. And half-life represents the amount of time that it takes for a material, usually a radioactive material, to decompose halfway. So however much you have sitting there, how much time will it take for the amount of that material to cut in half? Okay? So take a second, get those two words written down. And then we're going to move on and talk about graphs. So this over here, growth factor b greater than 1, this is actually what we did yesterday. And what we did yesterday, our graphs always look like this. Today we're looking at growth factors when b is between 0 and 1, so still positive, still bigger than 0, but smaller than 1. It's not going to be growing anymore. Okay, it's not going to be getting bigger. Instead, it's going getting smaller. So see, it's kind of that same curve. These aren't exactly identical, but they're both, this is exponential growth, this is exponential decay. Okay, but this one's getting smaller and smaller. Now notice it still has that same asymptote. I know it looks like it touches that x-axis, it really never does. And on both of these, the y-intercept is still at the a value. Okay, so whether you're going up or going down, it's always going to cross the y-axis at that starting value. Okay, this is kind of a recap of what we just talked about, so I'm going to go really quickly through it. But here's your model from yesterday. There's your formula, y equals ab to the. Okay, and this is just kind of giving you the restrictions on that. So a is always a positive number, okay, which is your starting value. If it's exponential decay, b is between 0 and 1. For a is your initial value, growth factor, and notice it's still called a growth factor even though you're getting smaller. Don't let that confuse you. And then there's your graph that still has the asymptote at the x-axis. So you still have that imaginary line that your graph is never going to cross. Y-intercept at 0a. That was on the previous slide as well. Okay, so let's talk about those growth factors. Yesterday we talked about how when you want to increase by a percentage, you have to add that percentage to 100 first. Okay? With exponential decay, and this right here, this is the big difference between today's stuff and yesterday's stuff, is that when we're decaying, instead of adding to 100, we want to subtract from 100. Okay, so if I'm losing 20% of whatever I have, that means I'm keeping 80%. All right, so just a couple of examples that I gave here for you. If in the problem it said something was decreasing by 12%, remember what you really care about is what percentage are you keeping. You're losing 12%. You don't care about what you're losing. You care about what you're keeping. So I'm going to do 100 minus 12 and get 88%. And then that is what's going to become my decimal that I want to actually put into my problem, which would be 0.88. So this is what I would put in as my b value. Okay? So key difference here, the thing that makes the difference between growth and decay, is whether you're adding or subtracting from 100%. If you were decreasing by 51%, I would do 100 minus 51 is 49%, and then make that into a decimal, 0.49. That's going to be what I put in for my B value, okay? Which means I'm keeping 49%. If I'm giving up 51%, I'm keeping 49. So what's left over, that's what I really care about here. Let's fly through one example real quickly. Used car dealers use this rule of thumb that the trade value, now notice this is not like the retail value, this is like what you would get if you were trading it in, decreases by 30% each year. So the first question says, if a car's value decreases by 30%, what value does it retain? Well, if the value of a car is 100% of its value and it loses 30%, that's going to leave you with 70%. Okay, so that's what you're keeping is 70%, and that's the number you really care about. So Sentador has a car worth $6,400. Write an equation that models the value of her car in years. So here is my A value. Okay, here's my initial value. And for my B value, I'm going to use that 70% that we said from up above. I'm going to do 0.70. And again, that came from this. To the power of X, where X is how many years since she bought it, or since now, I guess I should say. So I want to know how much will her car be worth in 3 years. That means I'm going to put 3 in for X. So I would do 6,400 times 0.70 to the power of 3. Again, make sure your answer makes sense here. I ended up with $2,195.20. So if she's losing 30% each year, her car's, oh, sorry, that's not a percentage. It's money. If she's losing 30% each year, she's keeping 70%. And so the car's value would go from $6,400 to $2,195 in 3 years. Okay, I know that seems like a lot, but 30% is a big chunk to lose every year. Now this says that Senta has owned the car for 2 years, which means she bought it 2 years ago. How much was it worth when she bought it? Well, if this is 2 years ago, we're really using a negative value for our X. I want to know how much was it worth 2 years prior to now. So I'm going to plug in a -2. And just remember that I would expect this number to be bigger than 6,400 because it lost value for those 2 years in between. So I'm still going to use 0.70, but I'm just going to go to the power of -2. Let's see where that gets us. And I come up with 13,061. And 22 cents. So that was the approximate trade-in value of the car 2 years ago when she first bought the car. Okay, so it's depreciated since then to reach this $6,000 mark, and then it would depreciate this much more 3 years from now. Okay, I do know there's one other example in your packet, but I'm going to skip over that one for today. I really think this is all you'll need to get going on your assignment. Your assignment today is Lesson Master 9-2B, and both of these assignments will be due tomorrow. So make sure you get those done. Blended class, first hour. Make sure you also use the online survey to submit which questions you want to see me do a lesson video for. Okay? Good luck, and if you have questions, feel free to email. I will be available tomorrow after school. I will not be around today.